So, we are going to discuss today in the lecture more about nucleation. I started this subject in the last part of the last lecture. So, as you know, phase transformations are basically controlled by nucleation and growth. So, whenever a new phase forms from a parent phase, basically the starting point is the nucleation. So, we will have a brief overview of nucleation, but at the same time I would like to tell that this will be a little bit overlap between solidification, which you are going to start at the beginning of the phase transformation, different types of phase transformation. So, solidification is obviously from this liquid to solid transformation. So, we are going to take examples of that to explain nucleation, and furthermore we are going to extend these things from a nucleation of a solid phase out of a solid. So, I am going to discuss most of the things in the using the blackboard today, so that you can understand nucleation is basically more of a mathematical way to understand than a physical significance. Physically, it means that we form a solid phase from a parent liquid or solid phase. It can be also from a vapor, but normally we do not discuss this transformation from vapor to solid. We always like to discuss from either liquid to a solid or solid to a solid. So, whenever a solid phase forms directly from a liquid, first thing we need to understand what is the driving force for its formation. Although we have discussed in detail about the thermodynamics of these transformations, but it is better we put it in a proper foundation. So, I am going to take a liquid to solid transformation and explain you why the driving force will arise and what are the conditions in which driving force will be available. So, let us go back to the board and see how we can use the thermodynamical formalism to explain the origin of driving force. As you know, if I consider, suppose if I consider a box containing liquid, and suppose under certain condition, experimental condition, a solid phase forms in the liquid. So, the question is that why at all the solid phase will form from the liquid? What is the driving force for its formation? This actually originates from the phi energy of solid and liquid phases. So, if I plot phi energy of a pure solid or liquid as a function of temperature, then the phi energy curves actually will look like this. Suppose this is for the liquid, this we write GL, and this is for the solid. So, therefore, at the melting temperature these two curves will has to cross over, because at the melting temperature they will have the same phi energies, otherwise there will be no coexistence of these two phases. So, because at the melting temperature these two phi energies cross over, therefore, the delta G, which is the difference of the phi energies of the solid or liquid, okay, this has to be S solid and liquid. So, if I write down Gs minus Gl, that difference is 0 at the melting temperature, because the values of the Gs and Gl are same at the melting temperature. So, as we go away from the Tm towards the high temperature, or if you go in, that is if you decrease the temperature from Tm to lower, there is always a gap between the phi energy curves. Now, these two phi energy curves are telling you relative positions of the phi energies of solid and liquid. So, therefore, only when I cool this liquid to a certain temperature below the melting temperature, I see there is a gap, and that gap is nothing but difference of phi energies of solid liquid, which is available to the system to create or to have phase transformation. And this temperature difference between melting temperature and any temperature to which we have cooled down the liquid is known as undercooling. So, therefore, these terms you must remember, this T delta T is known as undercooling in the literature, and that is defined as T mem minus T, because T is always less than Tm. And above the melting temperature, there is a driving force for solid to melt down. So, as we are discussing solid phase forming out of a liquid, so we should not discuss things happening above the melting temperature. So, as you clearly see, as I cool more and more the liquid, our driving force increases from this value to this value, or even this value to this value slowly. So, higher the undercooling, more is the driving force, as you clearly see. As you increase the delta T further, driving force is increasing. Now, can you just calculate the driving force in terms of undercooling in case of solidification? That is evident from this picture that as you increase the undercooling, driving force increases. But what is the scaling law? How the delta T actually affects exactly in terms of mathematical equations the undercooling? Well, as you know, G S is given by this equation. We have already discussed a lot, where S superscript stands for the solid, GL is the liquid free energy, where L stands for the liquid. So, therefore, the difference is delta H, which is nothing but Gs minus Gl, that is nothing but delta H, or we can write down actually S minus L T delta S, where delta H is nothing but Hs minus Hl, and delta S is Ss minus Sl. Remember that this H is the enthalpy and S is the entropy and T is the absolute temperature. So, therefore, I can write down at the melting temperature or at Tm, at T equal to Tm, that delta G is basically equal to 0, because at the melting temperature these two free energies will be same. So, thus I can write down delta H minus Tm delta S to be equal to 0, right. So, that gives me that delta S is equal to delta H by Tm. And you know, at the melting temperature, the heat which is evolved, which is corresponding to the enthalpy change, is nothing but the enthalpy latent heat of melting. So, therefore, I can write down this is L by Tm. Okay. So, now I can actually do a reverse mathematics to find out at any temperature T equal to T, what is the value of delta G. So, the delta G is nothing but delta H minus T delta S. So, I can write down the delta H minus T and replace this delta S by L divided by Tm. And at the, obviously here the solidification, the latent heat is of latent heat is evolved. So, therefore, delta H must be equal to latent heat here. So, I can write down T L by Tm. So, therefore, it is equal to L 1 minus T by Tm. As if you do the mathematics properly, delta H becomes, delta G becomes actually L delta T by Tm. So, as you clearly see, the delta G is proportional to delta T directly, because L is a constant and melting temperature is a constant for a particular system. So, more is the higher is the delta T value, higher is the value of delta G. So, as you undercool the liquid more, there will be more amount of delta G available to us or for the system to transform. So, that is the main driving force for the solidification to happen. Now, as I said you at the beginning, this liquid to solid transformation has two parts. One is the nucleation of the solid, another one is the growth of the solid. So, nucleation is what we are going to be discussing today. So, this driving force which is available to the system will be used to create this nucleus or nuclei rather in the liquid, and then the nuclei will grow to form the whole solid. That is the basic approach we use. So, how we can use this expression which is the available P energy to get some idea about the nucleation of this phase. Now, as if I look at it little bit different way, initially I have a complete liquid, you see here it is a complete liquid, then what happened, a solid, very tiny small piece of solid has formed in the liquid, and because of that there is a interface between solid and liquid. Remember, solid I have drawn like a hatch lines will be crystalline in nature. Okay. On the other hand, liquid is a complete random structure, and because of that the structural difference of between these two, even if there is no chemistry difference for the pure metals, this will lead to a interface between these two phases, and this interface because of virtue of its existence in the space will have certain energy, because it has a broken bonds at the interface. Thus, we have discussed a lot about these things in the few lectures previously. So, interface, because of the broken bonds between the solid and the liquid, there will be interfacial energy, and because it is related to the broken bonds in the interface, there will be positive energy of the system, and this energy must be provided by the system or by this kind of free energy available to the system to form this stable form of a nuclei. That is the idea. So, how do we do it in terms of mathematically? Let us suppose I have, which is the case, I have a spherical nucleus formed in the liquid, which is normally always consumed, because that makes the mathematics much easier, but it may not be the always case. The nucleus may be of different shapes, does not matter. If I have a solid nucleus formed in the liquid, okay, or let us suppose solid piece of a small tiny embryo which is formed in the liquid, which has not yet become nucleus, and this solid has a radius of r. Okay. If it has a radius of r, the total free energy of the system is nothing but a volume free energy change because of the solid to liquid transformation, that is because of these solid and liquid transformation happens at a certain level of undercooling, there is a free energy change because of that. So, thus volume free energy change is nothing but equal to 4/3 per r cube delta G V, that we always write. Why? Because the volume of these is basically spherical nucleus is 4/3 pi r cube, where r is the radius and G V is the free energy available to the system. And this always we write down minus. Why? Because this free energy you see here is the difference between a liquid and solid. This free energy is basically what? Is basically negative, because it tells you difference between solid minus liquid. That is what I have written, solid minus liquid. The solid has a lower free energy than the liquid, okay, and this is all, this liquid is negative, solid is positive here written. So, therefore, delta G V will be a negative sign, and this is must be added with the free energy of the interface, and we know that free energy of interface is equal to gamma SL multiplied by the surface area, and the surface area is 4 pi r square of a sphere. For a particular sphere of radius r, surface area is 4 pi r square, and it has to multiply the interfacial energy. So, if unit interfacial energy is equal to gamma SL, so that means this is equal to area multiplied by SL, or let us do it in a little bit different way. Let us suppose, before you go back to the equation you can actually get it, let us suppose this has a free energy of G1, this has a free energy of G2. Okay. So, therefore, if I write down properly here, let me just take it out all these things before you go back into that. So, therefore, the free energy difference between these two configurations is G2 minus G1. Okay. Now, what is G2 equal to? G2 is equal to Vs solid, obviously free energy of the solid. Okay. We can write down, this is volume is for V, VL GVL, that is free energy of liquid, plus the surface area between solid and liquid multiplied by gamma SL. So, therefore, G2 has phi the liquid multiplied the volume of the liquid, phi the solid multiplied the volume of the solid plus this interfacial area into interfacial energy. And what is G1 equal to? G1 is equal to again same thing VL GL, because G1 has only what? Only liquid, okay, plus, but this is not the correct. Why? Because the volume of solid plus liquid was the complete volume of the liquid. Remember that this is a complete volume. So, this was this form. So, therefore, this has come out. So, this must be subtracted or added if I have to do G1. So, now if I look at it completely, G2 minus G1 is what? This is again GL VL will get cancelled. So, therefore, I will write down Vs into G2 is GSB minus GSL plus ASL gamma SL. Am I right? This is what we get if you do the proper mathematics. So, that is the total free energy of the free difference of these two configurations. So, now what I have done, and this I will write down GT. Okay. So, what I have done here, same thing in this equation. I have assumed this particular species which is formed out of solid, out of liquid is nothing but a spherical shapes. So, if I have spherical shapes, then I write down this delta GV is solid minus liquid, therefore, this will be negative. As you see here, solid minus liquid, this is a negative, and V is basically 4/3 pi RQ, that is the volume of the solid pieces. Similarly, area plus area is 4 pi R square multiplied by the solid liquid interfacial energy. So, if you do completely mathematical way, that is what you will get. So, that is my total energy of this solid which is formed because of solid which is formed out of the liquid. Now, if I simply plot this equation, remember this equation has basically a single parameter R dependent. If we assume that gamma SL is isotropic and constant and assume delta GB is also a constant at fixed temperature. So, if I plot that equation here below, okay, let me just plot it here. Okay. So, what I am plotting here is this is x axis is R, y axis is G T, and three things I am plotting: GT, this one, let us suppose this one is C1 and this one is C2, so C1 comma C2, all of them I am plotting on this plot in different colors for your understanding, and all is a function of R, as you clearly see, all of them are function of R at a fixed temperature. So, let us first plot C2. Okay. C2 is basically R square dependent. What is the meaning of R square dependent? Basically, R square is nothing but a parabolic. Okay. So, this will look like this: C2 is proportional to R square. Okay. What about C1? C1 is basically RQ dependent, and so therefore, if I plot C1, this will look like this: C1 is proportional to RQ. And now, if you see GT is what? GT is a summation of these two terms, summation of this term and this term. First one is C2 is basically in positive term, which is proportional to R square. C1 is negative term proportional to RQ. Now, if I add these two up, this will look like this. Okay. So, that is basically GT, G subscript T. Okay. So, if I do that simply, what do I see? If I look at this curve, which is very interesting curve, actually this is basically genesis of homogeneous nucleation in this solid, in the liquid, of a solid phase. So, as you see here, as for small values of R, the total free energy system will increase. That is because for more values of R, the C2 term dominates. Okay. C1 is much lower than C2, therefore, the GT, the total free energy system, increases. Okay. But again, for very large values of R, the C1 terms dominates. That is what you can see here, it is dropping very fast at very large values of R. So, because of that, again the curve will go down. Curve will go down means the value will go down. So, therefore, in between, first there is a rise because of small values of R, then there is a decrease of the total free energy of the system as R increases. So, in between there is a maximum value, and this maximum value you always term as a critical value, what is known as R star in the literature. All of you have read these things. So, R star is what is nothing but a critical value of R at which this peak happens. So, first of all, this plot tells you the nucleation is a barrier or rather statistically barrier dependent phenomena. Okay. Here the atoms needs to cross a barrier to become a nucleus. So, R star is known as the critical value of R, below which everything is known as embryo. Only when one extra atom added to R star, the system will reduce energy and it will form nucleus. That is why I written nuclei. So, R star is basically known as a critical value of the del GT corresponding to GT. Okay. So, therefore, the GT value for this is known as delta G star, which is nothing but the critical value of GT, and it tells you that every system, whether it is a solid, liquid, gas or whatever, whenever there is a solid phase forming from the liquid or vapor or a solid, the formation of nucleus from the parent phase is basically a barrier dependent phenomena, and this is activation control rather, because the system has to pass over this barrier, cross over this barrier and reach the size of these critical size of these species more than R star, at least one atom extra than the R star, to become a nucleus, and then only it can grow further, because further as you increase the value of R, the energy of system will keep on decrease, and that is good for the system, because you want lower energy of system, all free energy of system always. Now, that is basically physical aspects of that. Now, simply whatever time I have in next 2-3 minutes, I can simply take this equation and do some mathematics also here. So, as you know, this is a peak value corresponding to R star. So, peak value means maximum. So, that means if I want to find out R star from this equation, I should apply the condition of maximization of this equation, right, because that is the value of maximization. So, if I do that, the condition for maximization is dt by dr, r is equal to R star to be equal to 0, and if you do the mathematics properly, that is very simple. So, R star will be minus twice gamma SL divided by delta GV. That is understandable. This is 4/3 pi, this will be 3 it will be 8 pi r square, and that is 8 pi r. So, 2 it will come, and then R star is basically twice gamma my GV. And similarly, if you want to cross check that this value of R star will lead to the second condition to be satisfied, because this is a maximum. So, therefore, this will be less than 0. Similarly, for this R star value, we can find out what is the barrier, activation control barrier, that will be equal to 16 by pi gamma SLQ by 3 delta GV square. Okay. So, obviously, these are all very simple equations, you can derive yourselves in your notebook. Now, R star must be converted in terms of undercooling. As you know, delta G is basically I know delta Gb for solidification is what? This is the latent rate delta T by Tm. So, therefore, I can get twice gamma SL Tm L delta T. Okay. The latent heat is always negative we consider, because that is a heat evolved during solidification. So, that is why this negative will get cancelled, okay. And then the R star will become a positive value. Similarly, G star is equal to 16 pi gamma SL Q divided by 3 and delta Gb square. So, therefore, this is L square delta T L square Tm square 1 by delta T square. So, if I know the undercooling, if I know the melting temperature and the latent heat, this latent heat is basically per unit per volume. That is why it is better to write volume, remember that this is not per mole, this is per volume. So, therefore, if I know the delta T undercooling for a particular experiment, I can calculate what is R star, what is G star. Normally, R star is couple of nanometer sizes, it contains about 20 to 100 atoms, and G star is the critical barrier, which can be very small actually, 10 to the minus 15 to minus 18 or 20 joule per cluster. That is very low value. So, in your assignments problems, you will find how to use these equations to find out different values. So, remember in the next lecture, that is what I am going to discuss. When I am talking about from a solid to liquid transformation, liquid to solid transformations, only thing I am assuming is what? There is interface between solid and liquid, correct? And because liquid is a basically cannot take up any shear, so any volume change because of solidification, it is very clear that solid will be more close packed structure than the liquid. So, because it is a more close packed structure, the volume, unit volume of solid and liquid will be differ, the densities of solid and liquid are not same. So, because of that there is a volume change, and this volume change in a liquid to solid transformation will not affect anything in the liquid, because liquid is basically cannot take up any shear. Therefore, even if there is a strain or there is a stress applied because of this volume change from the solid to liquid, this can be easily accommodated in the liquid, okay. That is very simple. But suppose instead I have a solid phase coming out from a solid, that means a solid nucleus forming in a solid, inside a solid, then there will be similarly there will be volume change, and this volume change will lead to stress at the interface, and this stress is, or rather strain actually, elastic strain will be available or will be leading to deform the matrix or the parent phase elastically, and these strains will have an effect in the value of the delta G R star and delta G star. That we will see in the next lecture.